Alright guys, in this video we're gonna learn how to calculate the Ecell free energy change and the equilibrium constant based on the reduction potentials of the electrodes. Here this is a concept map of chapter 18, and we're gonna look at this. We're gonna focus on the bottom half of this concept map, and I want to point out one thing. Here we have two ways to calculate the cell potential. You can use the reduction potential of the cathode plus the oxidation potential of anode to get the cell potential, or you can use the reduction potential of the cathode minus the reduction potential of anode to get the cell potential. Both ways are available for you, and you should get the same answer if you're using them correctly. I'm gonna show you how to use both of them in this question. Take a look at this problem. It's asking you to calculate the Ecell free energy change and the equilibrium constants for this reaction. Both reduction potentials are given. First step is you need to figure out what is oxidized, what is reduced. When you look at the oxidation state change, apparently iron is reduced. So reduction half reaction would be the 2 iron 3 plus, okay, plus 2 electrons to generate 2 iron 2 plus. Okay, and this is apparently going to be the cathode. So the reduction potential for cathode is iron 3 plus. It's given here, right? So iron 3 plus to iron 2 plus right here, and that is 0.77 volt. The oxidation would be the 2 iodide, give you one equivalent of iodine plus 2 electrons. And now let's think about it. If you want to use the first way to do the calculation to find out the Ecell, then you need to use the oxidation potential of iodide to iodine. Okay, this is the oxidation potential we need it. The reduction potential of iodine to iodide is given here. As we discussed in our lecture, if you want to get the oxidation potential from the reduction potential, the only thing you need to do is flip the sign. Okay, so this is the oxidation potential of iodide to iodine. Now, the first way to calculate the Ecell would be you add these two values together, 0.77 volts plus negative 0.54 volts. It gives you 0.23 volt. This is the first way. Now, how about the second way? The second way here to calculate the Ecell is to use the reduction potentials of both electrodes. Reduction potentials of both electrodes. Okay, so as you can see that we got the reduction potential of iodine 3 plus to iron 3 plus to iron 2 plus. Now here, if you want to use the second way, you stay as the reduction potential of iodide. That is positive 0.54 volt. Okay, so if you want to get the second way to do the calculation, that would be the reduction potential of the cathode 0.77 volts minus the reduction potential of the anode, which is right here, 0.54 volt. It is still give you 0.23 volt. Okay, so as you can see, the difference between these two methods is you are using, in the first way, you are using the reduction potential of the cathode and the oxidation potential of the anode. In the second method, you use both reduction potentials of the two electrodes. Okay, so that's the difference. All right, second part, how we calculate the delta G for this reaction. Second part, okay, so this is first part. As we can see from this concept map, this is the equation you need to use when you calculate the free energy change. Delta G equals to negative n. N is the number of the electron transferred. Based on these two half fractions, okay, if they are balanced, then you will see that the mole number of the electrons transferred is 2 mole of the electrons transferred times the Faraday constant, 96,500 joule per volt per mole of electrons, and times the Ecell, 0.23 volts. And if you do the calculation, it gives you a large number. It's negative 4.4 times 10 to the 4 joule. Okay, a large number. And based on the sign of the delta G, because it's negative, so it's a spontaneous reaction. When you have a negative delta G, as we can see, that Ecell would be a positive value. So if you want to decide whether this reaction is a spontaneous process or not, you can take a look at the sign of either Ecell or delta G. Okay? If this reaction gives you a positive cell potential, spontaneous process. Okay? All right. The last part of this question would be the equilibrium constant. We have two ways to calculate the equilibrium constant. You can either get the equilibrium constant from delta G, or use the Nernst equation to calculate the K, equilibrium constant, based on the cell potential. In this video, I'm going to use this Nernst equation. Cell potential is 0.23 volts. That equals to R 8.314 joule per K per mole. Okay. N, number of the electron transferred, we identified this number here. That would be 2 mole of the electrons times Faraday constant, 96,500 joule per volt per mole of the electrons. And then it's lane K. And if you do the calculation, okay, calculate the whole item here, divided this item on the two sides, you get this number, lane K equals to 17.92. And if you raise the two sides to the exponent position of E, that gives you this equation, and you can cancel the E and the lane here. That tells you that K equals to this value. Do this one on your calculator, you will get 6.0 times 10 to the 7. Again, it's a huge number. From this huge number, we can tell that this is a product favored reaction. It matches with our conclusion based on the delta G and the Ecell spontaneous process. It will go to the product side automatically. So this is a product favored reaction. I hope this video can demonstrate the connection between the two important parameters. Let me know if you have any questions. Thanks.